SwayamPrabha. Digital India. Educated India.
Yes, sir.
Okay, fine. The diameter of a metal shaft used in a disk drive unit, DISK DRIVE unit. The diameter of a metal shaft used in a disk drive unit is normally distributed. With a mean of 6.37 millimeter, the standard deviation of 12.7 into 10 to the minus 3 millimeter, that is 12.7 micrometer. The mean is 6.37 millimeter. The standard deviation is 12.7 micrometer. So they talk about micro. They also talk about tau. Okay. They also talk about tau. THOU. Tau means 1,000th of an inch. So they'll talk about the tolerance in tau. If you go to a shop, okay, not this shop in village area. I'm talking about a machine shop or a shop floor in a manufacturing company. They'll talk about tau. 2 tau, 3 tau, 7 tau means 1 tau is 1,000th of an inch. All right. So the problem goes like this. 9 o'clock, only 60 people are there. Yesterday we had 84. Okay. All right. The diameter of a metal shaft used in a disk drive unit is normally distributed with a mean of 6.37 millimeter and a standard deviation of 12.7 micrometer. The specifications on the shaft have been established. The specifications on the shaft have been established as 6.35 plus or minus 38 into 10 to the power of minus 3 millimeters. Okay. The specifications on the shaft have been established as 6.35 plus 38 into 10 to the power of minus 3 millimeter. Okay. One second, I have to take this call. So what should be the question?
Does the given specification lie within the...
No. Does the given specification lie within the... No, that is not the question. Just think about it. What can be the question?
Find the probability that one particular shaft that is chosen at random will have the diameter within this given specification.
Yeah, so, okay, you're coming close. Improve on this further.
Probability of having a shaft whose diameters don't meet the specifications.
Okay, so we'll make it more positive. All of you are close. So the question is, what is the fraction of the shafts produced which conform to the specification? Is that okay? So the question is like this: what fraction of the shafts produced? What fraction of the shafts produced? What fraction of the shafts produced conform? CONFORM. What fraction of the shafts produced conform to the specification? Is that okay? Yeah, there's a different way of saying. Who said that? Somebody said, what is a fraction which is not? So that is a pessimistic outlook. So let us look. Who was that?
Sir, Varshini.
Varshini. Okay, that's okay. That is a pessimistic outlook. Let us be an optimist early in the morning. Let's say what is a fraction of the shafts? We say, okay, they will lie within the limit. Just do it. Use the tables and do it. 5 minutes. So we are looking at so let's say this x. What is x1?
6.312. 88.
Okay.
Sir, 6.312 minus 6.37 by 12.7 into 10 power
6.37.
minus.
What?
That is the mean, right?
It is 6. Mean is how much?
6.37, sir.
Not
That
the,
is
that is true, sir.
that is what they specified itself,
The
right?
last step probability.
Just wait. Okay. So that is the mean was given to be how much here I gave
6.37.
Here also it's 6.3. Okay.
Sir,
Variance,
standard deviation
standard deviation also.
What is the standard deviation?
12.7 into 10 power minus
12.7.
What is this? Oh, okay. I mean this. So that is a tolerance. Huh? This is the tolerance. 12.7
7.
or what?
12.7 into 10.
Okay. So since we made a lot of corrections, let us make it very clear. So this is the mu and sigma. Okay. This is the mu and sigma of the distribution. This is the mu and sigma of the distribution. Okay. This is the lower limit and the upper limit. This lower limit and upper limit are given by the specification. Okay. So this specification is basically this shaft is used somewhere. It's basically production. So this is the production control. Okay. I mean post process. I mean only these limits are acceptable. But this mu and sigma are what the process can produce. Okay. What the process can produce is mu sigma and the normal distribution. What we can accept is given by this. So how much is the percentage which is produced, which can be accepted? So basically an engineering problem. Okay. So this is P equal to P of minus 4.6. What is it? What are you getting here?
Sir, Z minus 4.567.
Ah.
Uh, 1.417.
1.42.
So, how much is that?
0.9222.
So, yes, 0.4192. Plus 0.5. Huh? So, about 92% of the shafts made are fine. Fine means that all the shafts made are fine. 92% of the shafts made are fine according to the specs, according to the specification which is demanded. Okay, so this is the way you do quality control. Okay, so that 8% also you want to reduce further, then what you have to do is dimension tolerance has to be reduced. That means you should have a much better machine, and then you should have much better measuring accuracy. And okay, so increasingly that is a challenge. Okay, increasingly that is a challenge as everything has to be made more and more accurate. The tools and the machines required for making these things also have to be more and more modern. Okay, so more expensive and tighter tolerances and so on. All right.
Sir, how did you get 0.4190 plus 0.5?
You also get 0.9192, right?
The answer in the end I got the same, but how did you get that 0.5 plus?
Yeah, I did something. I don't know what I did. I did P of 1.4 plus P of 4.6. That's what is. How did you do it?
Sir, but P of.
One second. Just wait. I'm a little bit. Somebody's outside the door and. Yeah. I'm a little bit flustered since morning. Getting a call. Please tell me.
Sir, the
What was that?
P of Z less than 1.42 itself is 0.9222.
No, that's not what I did. No, I did something like this. Okay, what I did was I took the Gaussian. Okay, this is what we want. Okay, this plus 1.4. This is minus 4.6, correct? Is that okay?
Okay, sir.
Yes, sir. But minus 4.6 itself is almost zero, right? The probability.
The probability of that is 0. It's not even on the charts.
1.4 is 0.92.
Yeah.
Yeah. It is okay for me to. It is okay for me to find out this, and then that is also okay, right?
That is okay, sir. But in the end, like even when we're finding that area,
that doesn't matter. I can have multiple ways of finding. So I did this. That's all. How I got this 0.4192 and 0.5 is because I know what I have done. But this is correct. So what I have done is I have just left out this and I have calculated this. That's all. What is the problem?
So the thing that is there on
if you want a clean step, you put a step in between. Doesn't matter. But if you're an engineer, you should be able to do this way. That okay? What is wrong in this? And tell me.
nothing, sir. I just didn't understand how you got it.
So this is basically steps. JE, get out of that. Okay, it's a quick and smart way of doing things. It has be table will be minus. I have to do 1 minus this thing and okay. There are many ways of getting the. You remember Gauss 150 or 1 to 100. He wrote 150 and 51 to this thing. So what I did was it should be a large area. It should be very close to 1. Because anyway, this minus 4.6 is what is the sigma? Sigma is it is well below the 3 sigma whatever. So 1 should be almost 0.5. So you have to just take 0.5. Almost it is The full side of the left hand side is covered. And the right hand side, I have to find out what is on the other side of 1.42. Okay, the other side of 1.42, and so that's going to be only 0.1 or something. So it will be 0.4 plus 0.5 minus 0.1, which will be like 0.5 plus 0.4, which is like 0.91. Is that okay? If your school teachers or some maths cross statistics taught in a different way, it's okay. But I know how to get it. If you want to write some in between steps, you write. Is that okay? The answer is fine.
Sir. Yes.
Sir,
Okay.
sir,
Why are you hung up on this? Please tell me. Let's proceed. No.
sir, can you explain the question again, sir?
Can you explain the question again? You came late.
Sir, is x2 is 6.35 or 6.3 plus?
No, your audio is not okay. Can you come on chat? Can you come on the chat? Ujjal, can you come on the chat? X2 is 6.35.
So x2 is 3. You have written in the order 6.3 plus 0.038 millimeter, or is 6.35 or 6.3 plus?
No. Wait. 6.37 is the mean of the distribution. Okay. And 12.7 micrometer is the sigma of the distribution. Whenever you are calculating small z1 and small z2, this should be small z. Whenever you are calculating small z1 and small z2, you have to use only the mu and sigma. Okay. But to get the limits of x1 and x2, I have to work out from this, because that I have given it as 6.35. There are two sets of values. Are you getting the point? This 6.35 minus and 6.3, this is 6.35, right? 6.35 is it?
Yes, sir.
This 6.35 and minus and 6.35 plus have got nothing to do with the distribution. They are engineering. Only shafts between these two diameters will be accepted by the process. Is that okay? Now I have to convert these quantities and find out the probabilities. Now Ujjal asked me what is the doubt?
Yes, sir.
Don't get confused.
Sir,
This also looks like this. This has got nothing. This has got nothing to do with mu and sigma.
Where do you get 38 millimeter, 38 micrometer?
What is that?
38 micrometer is
38 micrometer is what?
38 micrometer
38 micrometer is what is specified. It is given in the question.
Yes,
38 micrometer is the tolerance which is specified by the manufacturer.
Sorry,
is that
sir.
okay?
I came late.
38 is what is specified by the dealer or whoever is buying this shaft.
Sir,
He will not accept.
doubt, sir. How do they measure the?
Such a small question. Why so many doubts? I thought it's a very simple statistical question. Why are you stuck in this question? Who is that? Hello?
Sir, how do they measure mean, sir? Experimentally, any techniques for measuring mean?
Who is speaking first? Okay. What is your so now it has got your mathematics is fine. You got the answer. It is fine. You are asking me a question outside the problem.
Yes,
correct?
sir. How?
Fine. First, no. Lot of people are asking question on 6.35 and all that. First, let's get it straight. You understood the problem. You worked out. You got the same numbers. Agree?
Yes, sir. I understood everything.
Wait. Now tell me what the question is, because the mic is also not okay. Tell me slowly.
How did they get
You are going close to the mic. Just go away from the mic.
measure it, sir?
Now
How did
tell
they
me.
measure that mean is 6.37? Any techniques?
Who has measured?
You said mean is 6.37. How did they arrive at that?
No, wait. The mean is 6.37 is basically that it can be arrived by what is the big deal? You 1,000 shafts are produced, you can find out the statistical analysis. What is the big deal in that? You take a micrometer, screw gauge, or you do some other thing and you do microscopy, whatever you want. What are the various ways of measuring a shaft diameter? You studied this is the first thing in measurement science, correct?
Yes, sir. Screw gauge.
Vernier caliper, micrometer gauge, millimeter gauge, whatever you want to use those gauges. And then work out the statistics. Every day they may be making thousands and thousands. Then take the statistical average. What is so difficult? See, Suraj Kumar every day is measuring temperature. If he measures the temperature, ambient temperature, within 11 o'clock, 11:30, 100 times, the data logger will, every 5 seconds, it will measure. I can take an average. What is the problem in taking the average? Even the computer will directly give the average. What is bothering you? Why is it so difficult to measure the average, according to you? Measuring the true value is is difficult because we don't know what the true value is. But measuring the average is not a big deal. True value is truth is something which we don't know. That's what Gauss also was worried 200 years back. Now Pawan, is it okay? Hello.
Okay, sir.
Okay, all right. Measuring the mean and standard deviation is not a big deal. We are doing it for 200 years. Okay. Okay. Anyway, a simple question led to so many discussion. Is that okay? That's all right. Okay. Now we have to understand an important concept called the maximum likelihood estimation. Okay. The maximum likelihood estimation is basically some funda concept was proposed by Gauss, and then it's a very good thing. So it's very that Gauss is able to think about these things 200 years back. It's such a revelation. Okay, it's a breath of fresh air. Okay. Now let us go to the straight line fit. Y equal to ax plus b. Okay, this is a proposal to fit a straight line versus of y, x versus y, and some measurements are done. So x1, xn, y1, yn. So y equal to ax plus b is a proposal. This proposal can come from the forward model. This proposal can come from common sense. This proposal can come from theory. This proposal can come from prior knowledge. Look at the first problem in this course, where the proposal of temperature varying linearly with x came because of a solution to the forward model of one-dimensional steady-state conduction with constant properties, with no heat generation in a slab, which reduced to d square t by dx equal to 0 upon integration dt by dx equal to a, further integration t equal to ax plus b. Now, if it is a regular heat transfer class, we will go tell you at x equal to 0, x equal to what the temperatures are. You will get A and B, then you will use Fourier's law, you will get the heat flux, get 8 marks, whatever, get your grade and proceed. Now, the problem is I have a lot of measurements, which is the way it is done. So, if you're a PhD student or you're in a company, you got a lot of measurements and you want to find out what the heat transfer rate is across the medium. So, the problem is more difficult than you imagine because the straight line passes through only 2 points. I've got more points. Therefore, the concept of a best comes. The best could be several things. One best could be like this. So there is so let us say So let us say that this is X and this is Y, and your proposal is to fit a straight line. One thing is, I can take a scale. And I do something like this. Okay, I do something like this. So this is correct. This is possible, right? So you don't know the statistics. But you know that you're trying to get one line because you know that the solution is a line. It's not a curve or polynomial. So if you do like this, it's absolutely wrong. You don't know any heat transfer. Temperature will never vary like this in nature, because the thermal conductivity has to go to a tortuous variation of K equal to Ax plus Bx equal to Cx plus D. There is no material because against common sense. Mathematics can say so many things. It is mathematically possible. Mathematics is not life. Reality is different. So we should not do that. Okay. Now, compared to a mathematician, you have common sense, so you do a little better. So without doing least squares, you do like this. So this can be called as the Desi line. Let's say, just to make it more, okay. This is called a Desi line. I mean, this is Desi approach. So I will give it a more scientific name. This is called the visual best. But the visual best is not always possible because y is a function of only one variable, and if it is not linear, you can't do the visual best and so on. Of course, y equal to ax to the power of b, you can take ln y equal to ln a plus b ln x, ln y equal to capital Y, and ln x equal to capital X, and y equal to ax plus b. You can still, and then one could be take anti-log of b, blah blah blah, all that. The a you can take it, and you can do some masala, all that. So you can play the game only up to a certain level. Okay. If it is non-linear, if it is multiple variables, all that, you need some tools. Okay, be that as it may. For starters, if you know that y equal to ax plus b, and you know you are terribly woefully short of time, you can get the visual best, or this thing can be easily done. Excel will do it for you. Okay, but we are tracing the historical origins of the least squares and all that. Okay, so now I want to do better than this. I want to do better than the visual. I want to actually find out based on some principle, based on the laws of probability. Now, what I'm saying is, let us assume, so this is 1, 2, 3, and 4. Okay. Let us assume that the measurement error, so x is the location and y is the temperature. Let us assume that the measurement errors are normally distributed, which is fine. You remember Gauss, when he measured the distance from the gymnasium to his house, always he was getting a different number. So they are normally distributed. The measurement errors are normally distributed with mu sigma. Okay, with mu and sigma. Okay, further mu equal to 0. The errors have a 0 mean. If the mean of the error is not 0, then it is a biased measurement. Then if you know that if the mean is not 0, you will correct it. That is, on a weighing machine, if you switch on, if it shows 1 kg, then that is something you know. It is not a statistical error. Then if you measure something, you will always subtract that 1 kg. Okay, so you can always reduce that, even if the mean is, that is called a 0 error. You can make a 0 correction. Okay, but around that 0, whatever it is, even if the default is 1, around the 1, the errors are normally distributed. So you just correct your bias. So in engineering, in science, whenever we have a measurement, first we will do bias correction. There will be a lot of positive bias or negative bias. How do we calculate the bias itself? There should be some other instrument which is more accurate than this. Therefore, if this is not the truth, something else is assumed to be the truth. How do you get that as the truth? So therefore, there is a lower truth, there is intermediate truth, there are higher truth, and so on. So national conference on weights and measures, international conference on weights and measures, blah 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 blah. Finally, what is a meter? What is a second? So some rod is maintained in Paris at this temperature, it is cooled, heated, it is maintained at that pressure, blah 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 blah, all that. So from that international standard, what flows is it comes to the national standards and the state standard, regional standards, and all that. But nowadays we don't worry so much. Okay, this scale, whatever it is saying, somebody must have taken care of all that. We don't even go that far. Okay, if it says 5 centimeter, it should be 5 centimeters. Okay, so we believe that somebody must have calibrated that. All right. So the mean is 0 and the standard deviation is sigma. Now, the probability, what's the arguments? These are all proposed by Gauss. The probability of getting y1 for an assumed value of a and b, but now the goal is to get y equal to ax plus b is the proposal. A, B is as yet unknown. A, B is as yet unknown. So the probability of getting y1 given a, b is nothing but 1 by root of 2 pi sigma square e to the power of minus y1 minus ax1 plus b whole square by 2 sigma square. Is it okay? So this is the probability of getting y1 for a given x1 and for an assumed a and b. That a and b can be, you can assume a and b whichever way you want. Okay, you can assume a and b. And, all right. Now, so this equation, the probability of getting y2 for a assumed value of a and b. So this is called as a conditional probability. Okay, this is called the conditional probability. Probability of y for a given assumed set of a and b. Okay, e to the power of minus y2 minus ax2 minus b whole square by 2 sigma square. Like that, I can get individual probabilities. I can get the individual probabilities of getting 0.1, 0.2, 0.3, 0.4. Now, the probability of simultaneously getting, some mistake is there. The probability of getting simultaneously P1, P2 up to Pn is simply P equal to P1 into P2 up to Pn. Okay. Why is it so? Okay. So this is the I call this as the total probability I'm just looking at the notes to check the consistency of the notation. The total probability is P of y1 to yn for a given value of AB. Now I'm saying that it is equal to this. Okay. Why is it so? One, two. Why is it so? Because they're all independent. Therefore, this L is called the joint probability, the joint probability density function. The joint probability density function. So it is a product of the probability if they're independent event, and you want all the events to take place. So I will toss a fair coin 3 times, and I want to get the head all the time. Oh, this is tough. What is the probability of getting a head? Half. I want to toss 2 times. Both the times I want to get head. Half into half. I want to toss it 10 times. All the 10 times I want to get head. Half into half into half into half into half into. So once you make it tougher and tougher and tougher, so 100 times I want to toss the coin. All the 100 times I want to get 100. You will get an impossible probability 1 by 2 to the power of 100, which will be like so many zeros. Because already there is a half. Second time there is another half. Third time there is second half. Therefore, the probability of P1, you want to get P1. The same you want to get P2, you want to get P3. Each of them is a function of A and B. Let's not worry about what is within that. You will assume some A and B, X, Y. You'll work out the number. Don't get worried about the number. The funda is more important. So it is a P1 into P2 into P3. So therefore, the L is nothing but product of the probabilities. So which is mathematically denoted by capital Pi. Okay. What is this equation number? Huh? What is the equation number? Hey, am I audible?
Yes, sir.
What is the equation number? Can somebody tell me the equation number?
21.
21. Oh, no. Today I started with 1, 2, 3, 4, 5. No? Are you writing or not? Somebody should be writing. Varshini, what is it?
Sir, I'm not marking it.
You are not writing. Okay. I'll put some 5. Doesn't matter. Tomorrow in your class notes, if you don't get 4, don't blame me. Where did sir write 4? Huh? All right. Therefore, L is nothing but okay. Now, let us look at
Sir, what is L? I mean, what does L stand for anything?
L stands for the total probability. What is the total probability of getting all the points?
Okay.
What is the total probability? Okay. Okay. So let us, Z is not a good thing. Let us look at, let us define some other Z already we used. Y, X already used. Okay, I'll put some 5. Huh? Okay. 5 minus 2 ln L. Just do minus 2 ln L. So therefore 5 will be equal to 5 will be equal to N ln 2 pi sigma square plus okay. Now what's the arguments? Gauss asked, the question Carl Gauss posed to himself was, what should be the value of A and B which will maximize the total probability L? I come again. What should be the value of A and B which will maximize the total probability L? If you answer that question, and get the estimate of A and B, it is the most likely answer because that will maximize most likely from the viewpoint of probability. So, if you what A, B will max L, this is the question. The answer to that question is you find out, okay? That will be the maximum likelihood estimate. Now, you don't even need least squares. Please note that it will lead to least squares is a corollary. But now let us stay with this. Let us stay with what? Okay, I can erase this, right? So let us stay with this. Now, it is possible for me, okay, for so it should be the same A, for example. I'm just giving you for depiction. Don't think that this. I'm just saying you can draw various curves of B1, B2. Find out at what value of A this L will be a maximum. Like that, you can have a plot of this with A1, A2, A3. This is just a two-dimensional depiction. If there is a single parameter, straight away you can. Therefore, if you do this, you can find out for which value of A and B, for which value of A and B, the L will be a maximum. Okay. So, in this day and age, for example, let's say values. 20 values. You take 400 pairs of A and B and work out the L, put it in descending order in Excel and get the value. And get the value, which will get the value of the pair or get the values of A and B, which will maximize L. This does away with least square, this thing, calculus, all that. So this is a brute computational approach. This, if you do it this way, what you're doing is computational statistics. If you do it this way, it is simply statistics. It came from probability. But if you're working out the probabilities, you are a statistician for various values of the data. If you're just looking at the concept and leaving it and your work is entirely restricted to paper and pencil, you're in probability. When you apply to actual data, you're working out the numbers. You're taking raw data. You're looking at temperature. You're looking at sales. You're looking at demand. You're looking at rainfall. You're looking at consumption. Then you're working with statistics. What is that L? If you write this, if you're that high priest, okay, you're the high priest and say you maximize L, you get the answer. If you leave it there, leave it at that place, you are a probabilist. Now for your actual heat transfer problem, if you apply it, then you become a statistician. Is that okay? So this is called computational statistics. So this computational statistics has really taken on in the last 30-40 years because a lot of algorithms for sampling. Obviously, there can be scientific ways of sampling A and B. That's what I'm going to teach you in next month. Okay, I'll probably teach you March or April. So there are scientific ways of generating samples. It is not like a helter-skelter. I will not choose A and B from 0 to infinity as a mathematician will do. I am an engineer. I know what are the values of A and B because A is likely to be, what is A? T equal to AX plus B, dt by dx equal to A. The Q is equal to minus K dt by dx. Q equal to minus Ka. Therefore, A equal to Q by A. For that slab, it won't be in megawatts. It will not be in microwatts or milliwatts. I know that in that slab, it will be a few hundreds of watts. If it is only a few hundreds of watts per meter square, the thermal conductivity is K. I know what is an approximate ballpark, approximate value of A. I will not stupidly vary A from 0 to infinity. That may be a purist approach, mathematician's approach. Why do I care? Why should I be a purist? I'm an engineer. I want the answer. I will try to use the smartest way possible to get to the solution. So there can be bounds on the values of A and B, which cannot be guided by mathematics. The bounds on A and B, what are the samples you have to take? That has to be guided by your knowledge of heat transfer, by knowledge of your domain. Pure data science would not work. Even if you are a computational statistician, if you want to do really smart work, you should have the knowledge in that particular domain. Therefore, a pure computer statistician will not be able to solve problems in all the fields. He may do it in 1 or 2 fields, but there will be a smart guy in electrical engineering or ocean engineering who can do it much better than him. What he or she has to do is only understand the basics of this. If he's very strong in the subject, he can narrow down A and B. He can get it at a fraction of time, which a big data scientist will get. You understand? However, having said that, if a person who is very strong in his domain also learns data science, he'll be a leader in his field or her field. Is the funda clear? And see, if you're good in heat transfer, if you're good in mechanical engineering, what is a big deal? We will learn data science, we will learn statistics, we will help everybody. Is that okay? So don't be afraid of all this. If you can learn X or Y, if you're smart, we can learn Z. We can also learn beta, gamma, whatever. Okay. There should be a will to learn, that's all. All right. Now, so this is computational statistics. But what we are doing is, we are not doing this now here. We are not doing this now here. This can be reserved for problems in which it becomes very difficult to proceed further mathematically. Okay. Now, what I can do is, what A and B will maximize L will be what AB will minimize phi. Therefore, the phi is a function only of A and B. Okay. Therefore, if I put dou phi by dou A equal to 0, dou phi by dou B equal to 0, then anyway, the first term, n is a constant, sigma square is a constant, this one will not have any effect. So sigma square is also constant. Dou phi by dou A, please note that here it is there. Okay. This is there. So this becomes 0. This sigma square is a constant. So this gives exactly the same equations. Exactly the same equations. As the least square regression. This was something which Legendary did not find out. Okay. Minimize R. Minimize sigma R squared. Okay. 1805. Legendary did it. At least according to the book which you saw yesterday, Gauss got this answer 10 years back, but he did not publish. But Gauss went one step further. He was able to link the least square minimization to the original idea of a Gaussian distribution, the original idea of a probability, a conditional probability, a joint probability density. Therefore, if you get the maximum likelihood, it is akin to, or it is equivalent to, it is the same as getting the least square minimization. So Gauss forever remains the prince of mathematics. So that he is able to think so much. Even when he was just a schoolboy, he didn't even get his PhD. His PhD thesis is available. You just download it. So some 43 pages, but it is in German language. So he wrote his PhD at the age of 22. It's just some 43 pages. It is there. I saw it in ETH website yesterday. ETH Zurich. Bibliothek in Europe means bibliothek is the library. They have a free PDF. Of course, it is not in English, but we found out that he has done something in arithmetic. All right. So now the link between probability and statistics, the link between least square minimization and maximum likelihood estimation is, that picture is 210 years old, thanks to Gauss. Now, there are a lot of subtle things which can still be figured out. Please note that the sigma square can still be an unknown in the problem, and you can do dou phi by dou sigma square equal to 0. And apart from A and B, you can also pull out sigma square of the sigma square. Therefore, even if you don't know the sigma square, but if you know that it is normally distributed as a post-process quantity, you can actually get a figure. You can actually figure out what is the standard deviation of the measurement error likely to be. Now, in this case, we assume that AX plus B, when you put this, it is a true solution to the problem. If you're doing a CFD solution or if you're doing a numerical solution, there can be an error generated in the solution also. Therefore, this R square will be sum total of the error in the forward model and the measurements put together. They have to be combined. Now we assume that there is no error in the forward model because it's just AX plus B. So the error is only in the measurement. And even if the sigma square is not known, it is possible for you to pull out. Then comes the killer stroke. The killer stroke is the sigma can be taken inside, and as some Anand Kishore asked me someday, you can actually take one sigma, or 2 sigma 3, and you can actually work it out for various values of sigma. If you know for a fact that the first thermocouple, the second thermocouple, third thermocouple, they all have different errors, they can still be accommodated. So many things are possible. And this y equal to ax minus b is only an excuse. If you know any other forward model, you just put it. And it can be double summation, triple summation, whatever you want. You can sum it over x, you can sum it over time. So you could have a spatial integration. It could be a spatially and temporally varying temperature, voltage, seepage, flood, rainwater, rainfall, whatever be the quantity. If there is a forward model, we will try to do this. The idea of a pure data science approach to this could also be like people like Professor S. Balaji is working. So he's also my collaborator in some of these things. So independently he's working on certain ideas. It's basically, if there is a lot of previous data itself, that from the data itself, we can build a forward model. Therefore, the d squared t by dx squared equal to 0 itself is not required. That is a forward step. For that, a lot of data are required. For engineering, it may be difficult to generate that kind of data. But there are a set of problems in which data science can help. Okay, so I think from a pure perspective of, so we have to keep pace with the time. So it is good that you're able to, you have taken this course, and last 10 classes, I'm teaching all the classical techniques. S. Balaji teaches the neural network and so on. And regardless of whether you're doing a dual degree in data science or not, at least you'll have a flavor of, you will appreciate what are the things that are going on in inverse problem, what are the things going on in data science, how to look at data from a statistical perspective, from a probability perspective, from a belief perspective, and so on. Can I stop here? We'll meet on Monday. Any doubts? I hope I'm still audible. Can somebody? I don't become like the NUS prof. Thank God. Okay. So today was an exciting lecture because I have a great respect for this Gauss that he's able to think so much. Huh? Okay. So at least we are fortunate that we're able to study. All right. Chalo. Take care.